Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Here's today's topic: using OCS in a 12-volt DC environment. Now, today's topic was by request from Bob Lindbergh from Pacific Fisherman Shipyard. Thanks, Bob, for that request. So, Bob wanted to know what were some of the implications of using the OCS in a mobile environment or a 12-volt environment, not only from the standpoint of power, but also approvals, and maybe what are some of the features that are popular in mobile applications versus maybe your standard industrial applications. So we're going to try and cover as much of that today as we can, not just for Bob's benefit, but also for yours. Now, I am flying solo again today, at least on air. No co-host today, but we are fortunate enough, if you're watching this live, that we have Nate Beachy, our applications engineer extraordinaire, standing by to answer your live questions in the chat section. Also, if you're watching on replay, one of us will get back to you as soon as we can, whether it's myself or Nate, maybe Casey, our product manager, heck, maybe even Tim Brandt, our tech support manager. So let's go ahead and dive into today's topic. Using OCS in a 12-volt environment. Here's how we're breaking down today's topic. We're going to talk about some common 12-volt applications. Of course, it's important for you to know which Horner products are compatible with 12-volt DC. We're going to talk about some general considerations of 12-volt applications, as well as some unique issues that crop up and some solutions for those issues. We're going to talk about popular features for 12-volt applications, and we're going to spend plenty of time doing demonstrations. All right, here we go. What are some common 12-volt DC applications? Well, really, any application that's battery powered from a 12-volt standpoint is, of course, a 12-volt application. Mobile applications are probably the most common applications with a 12-volt environment. Marine applications also, as well as solar applications. Now, what you'll find in all of these cases is that some applications are 12 volts and some other applications in these same areas are 24 volts. For example, automotive applications, of course, are about as common a mobile application as you can come by. But with the advent and popularity of electric vehicles, there's a lot more 24 volts being used in the automobile these days than ever before. So it's not automatically a 12-volt application if it's automotive, for instance. So always check to see, in your particular case, what the voltage is before you proceed, of course. Which OCS products are compatible with 12 volts DC? And basically, when we mean compatible, we mean two things. One is that we mean they have a wide voltage range, typically 10 to 30 volts DC on the power supply side. And secondly, for any inputs, digital inputs that are part of the OCS, are those inputs compatible with 12 volt DC signals? In other words, is the turn on thresholds such that you'll see an input turn on as appropriate with a 12 volt type input. So those are the two requirements that kind of causes us to say, yes, these OCS are 12 volt compatible. And basically all the models you see on the screen there, plus the RCC, are the models that meet these requirements. And if there's other models that you're interested in using, well, certainly you can use those models, but only if you use some sort of a power supply or DC to DC converter to take the 12 volt input from the supply power up to 24 volts. But if you're not looking to do that, then you'd be looking at these products here on the screen, the X5 and X10 that are part of the micro OCS family, the XLE and XLT, as well as the XL series and the new XL Prime series. If you're talking about expansion I/O, what if you need to add some additional I/O and you're looking for 12 volt compatible I/O? Well, there your choices are a little more limited than normal. You're basically looking at Smart Block, Smart Mod, as well as the new OCS I/O that we'll be releasing this summer. So these products, again, are compatible with 12-volt supply power, and they have the appropriate on-off thresholds to be supportive of 12-volt inputs. Let's talk about some other considerations before we do a deep dive into some of the voltage issues that can occur. Let's start with approvals. What about UL? As all of you probably know, or at least most of you, UL is pretty much an accepted requirement for industrial automation applications, right? If it's an industrial automation application, generally there's a high percentage of chance that UL is going to be a requirement. And the way that OCS handles UL is like many other automation components. That is, it requires a Class 2 power supply to be used for UL approval. Now, what is a Class 2 power supply? Well, basically, it's a power supply whose energy is limited to kind of limit some of the situations that can cause problems. And I believe the limit is about 92 watts total. And what you'll find is that Class 2 power supplies are not common in 12-volt systems. I think I've seen one Class 2 power supply for DC, and it was not compatible with 12 volts. It was requiring of 24 volts on the supply side. But the good news is that in the mobile arena, which is a lion's share of the applications, UL is not a typical requirement. So therefore, the lack of UL, because of a lack of a Class 2 power supply, will not be a problem nearly always. What about ABS? ABS stands for the American Bureau of Shipping. It's another approvals body. It's also a very common requirement, at least in North America, for marine applications. And plenty of marine applications are 12 volts. Others are also 24 volts as well. And we have several OCS products which do carry ABS approval, namely the most popular being the XL4 and the XL7. So the good news is that you do have ABS approval for those applications that are marine-based, that are 12-volt powered, as long as you're not using the OCS for propulsion purposes. All right, so ABS is not a problem with 12 volts. The OCS models that are compatible with ABS are compatible both with 12 volt or 24 volt voltages for marine. Another general consideration is the fact that sometimes when you're talking about battery voltages specifically, it can be useful to monitor the voltage, the supply voltage, using an OCS analog input. That way you can do things like maybe set some alarm conditions when the voltage starts to creep to a lower level, or maybe when it starts to creep above your expected level. That's two of the benefits of having monitoring of the supply voltage. Another benefit is data logging. You can be data logging on however frequently you want the supply voltage, so you can go back and take a look at how does it look in general in the past, for instance. You may be asking, how are we going to be monitoring supply voltage, which could be anywhere between, let's say, 9 volts and 16 volts as typical. How are we going to be able to monitor that when we have a 0 to 10 volt limit on our analog inputs on the OCS? Well, basically, we can do that using a simple voltage divider. And this is typically what we do in those applications internally when we've got 12 volt testing that we're doing. We'll use a voltage divider. And because of the typical range you see with 12 volt systems, what we usually do is we use a voltage divider where both of the resistors are equal. And then we run the center point between the resistors into the analog input. And now effectively we're measuring half the voltage, and then we can use some simple math to be able to determine what the supply voltage is, right? So if there is 12 volts of supply voltage, we're going to see 6 volts on the analog input. If there's 20 volts on the supply voltage, we're going to see 10 volts on the analog input. So that's a pretty typical way that we can use to monitor the supply voltage. The first demo I'm going to do for you today is showing you just that. So on my bench, I've got the circuit that you see there on the screen. So I've got a variable DC supply that I can vary, say, up to 20 volts. And I've got a voltage divider using 10K ohm quarter watt resistors. And from the center point of those resistors, I've run that into an analog input on an XL4, and I'm monitoring the supply voltage. remember, the benefit of doing this is for things like alarming and data logging. So let me first show you in Cscape some of the setup that I am doing, and then I'll show you what it looks like on the bench. Okay, so let's fire up Cscape here. We're going to start from the hardware configuration. Now, before I even configured the hardware in Cscape, because I'm using a XL4 Model 2, there are jumpers that I have to move to support 0 to 10 volts on the input range. The default is 4 to 20 milliamp, and the Model 2 is one of those models that requires a jumper movement to support 0 to 10 volt. So the first thing I did was pull off the back cover, move the jumper for channel 1, and then put the back cover back on. But next I fired up Cscape and went to the hardware configuration, looked in the local I/O tab, and then hit config, module setup, and then on the analog input side, this is where I set the voltage range or the input range to 0 to 10 volts. I also applied a little bit of filtering just to steady the readings out a bit. This is a fairly low level of filtering that I've assigned, and that's pretty much all the configuration that I need to do. Next, I wanted to set up some alarm conditions so that when the voltage, say, hit 17 volts, that would indicate, you know, the voltage is higher than I want. That's a high alarm condition. When the voltage hits 11 volts, that's lower than I'd prefer. I want to know when it hits 11 volts. Because remember, the OCS is going to power off somewhere a little bit less than 10 volts. So I want to have some warning if the voltage starts creeping downwards on me. Let's go into the operator interface or the graphics editing section of Cscape, pull up config alarm, and then you'll see I've assigned up to 16 alarms, and I've assigned them to a variable based array. All right, and I've just so far for demonstration purposes, I've set a undervoltage alarm at 11 volts from a descriptive standpoint and an overvoltage alarm at 17 volts. But I need to add some logic to be able to implement those alarms, so I'll show those to you here. Now, basically, this is where I do some scaling of my analog input from counts to voltage. All right, and I'll come back to this in a minute. But from an alarm standpoint, here's my undervoltage alarm, which is the first member of the array, the alarm array. Basically, I'm saying if I hit 11 volts, I'm going to call that an undervoltage alarm. And then if I get back above 11.2, I'm going to call that a return to normal. On the high voltage side, if I achieve 17 volts, that's a high alarm. If I get back below 16.8, that's a return to normal. Now, how did I take the actual analog counts and convert them over to volt? I went ahead and I only needed two function blocks to do that. First of all, I think most of you know that the analog inputs come in as integers, scaled from 0 to 32,000. So we need to convert that over to a floating point value or a real value. So I did a conversion function to take a variable that was mapped to analog input 1, okay, and over to another variable that is a real type variable. So I used a conversion function. Once I did that, then it was just a matter of doing a scaling function. Now, in general, the scaling that I started with was 0 to 32,000 on the analog side, goes 0 to 20 volts on the voltage side, okay? Now, you're saying these numbers don't look anything like what you just talked about. Well, that's because I went ahead and took a digital voltmeter and I optimized the scaling for between 5 volts and 16 volts. All right, it scales outside those limits, but I optimized the accuracy between those 2 points. You'll see why later. But anyway, so that's the logic that was required on the Cscape side to do the scaling and to set up the alarming. I also could have set up data logging if I wanted to, which I would typically recommend for a 12-volt application. Just a good idea to kind of monitor your supply voltage on a periodic basis at least. Okay, let's take a look at the bench. All right, so here's my bench. So this is my variable supply, and it ranges up to 20 volts and down to just a few volts. It actually can go higher than 20, but I'm just going to show it up to 20 today. And then here's my XL4, which effectively has the analog circuitry connected to a voltage divider, which is off the screen. So I don't have that shown on the camera, obviously. But I've got that 10K voltage divider with two 10K resistors running into analog input number 1. And as I vary the supply voltage, you should be able to see that the OCS is monitoring it right alongside. Now, you'll see once I get it to 17 volts, I should have an alarm condition, right? So I continue to move this up. Yep, I've got an alarm condition. I'm going to go ahead and acknowledge that alarm. Okay. And then as my voltage drops below 16.8, you can see I've returned to normal. Similarly, on the low end, as I move down here towards 11 volts, you should see another alarm. Okay, there it is. I'll go ahead and acknowledge it. And then when I get up over 11.2, I'm clearing the alarm. Again, I just added some hysteresis on both the low and the high alarms just so I don't have the chance of sitting there dithering the alarm on and off. The voltage range for the XL4, and it's true with just about all of the OCS products, is 10 to 30 volts DC. Somewhere below 10 volts, it's going to go ahead and not have enough voltage to be able to operate. So I'm going to go ahead and see if we can find that point here. Okay, so at some point when I get down below 10, we're going to see the OCS not only be in an alarm condition, but we're going to see the OCS go ahead and power down. We're still going about 9.5 volts. Again, 10 is the spec. Oh, there we go. We got down around 9.3 and that was all she wrote. Okay, and then when I get back up above around 10, I've bumped it all the way up to 13. It reboots, and it's rebooting now. It's just the screen is dark for the first couple seconds of the reboot process. Okay, so that should give you an idea of what we're talking about in terms of the ability to monitor the input voltage, which can be valuable when you're depending on low levels like that and you're depending on a battery, for instance. It's valuable to go ahead and monitor that. Let's go ahead and continue on with our material now. During the next portion of our presentation, we're going to talk about 3 unique 12-volt DC issues that you run into in mobile applications for sure. Okay, and they're all related to the fact that you've got a battery and an alternator very often in these systems. The 3 issues we're going to talk about one at a time are battery drain, which is a low voltage condition, engine cranking, which is another low voltage condition, and then something called load dump, which is a high voltage condition, or specifically a high transient voltage condition. All right, let's take a look at these one at a time. Let's start with the battery drain issue. This is one we can all relate to. It's a low voltage condition. We've all left the lights on at some point and drained our batteries in our automobiles, haven't we? But the specific issue I'm talking about here basically is a scenario where, again, somebody left the lights on, let's say, or some systems were left on, and the battery is not charging, the battery is discharging because of these loads. And let's say that the OCS is one of the devices that has been left on, and the battery is not charging, and so what's happening is the battery is slowly draining. The voltage is slowly dropping, and at some point it's going to approach the OCS threshold, somewhere between 9 and 10 volts. At that point, the OCS is going to power down, but when the OCS power down, it's very possible that the reduction in load of the OCS being off is enough for the battery voltage to go back up again a little bit, potentially enough for the OCS to try and turn back on again, and then of course the voltage drops, and it's a vicious cycle of the OCS continuously trying to reboot at the point at which the battery voltage is kind of slowly falling between the threshold voltages of the OCS. This is a condition that can occur, a condition that we'd like to potentially alleviate if possible. So one of the ways to alleviate this issue is by using a DC to DC converter. So a DC to DC converter is a power supply that can be used to convert one DC voltage to another. And specifically in this case, we're going to use probably a DC to DC converter that's going to convert 12 volts up to 24 volts. One of the reasons why this can actually help is because a lot of DC to DC converters, at least ones that are pretty good quality, they have some hysteresis built into them, so that they shut down at a lower voltage than they turn on. So on the screen there, I'm showing the graph, the shutdown and turn on graph for a Pulse DC to DC converter. Pulse is a very reputable manufacturer of power supplies, and they have a line of DC to DC converters. And as you can see here, the Pulse power supply is going to shut down when the voltage drops below 7.2, but it's not going to turn on again until the voltage goes up above 8.4 or maybe 8.7. So that little bit of hysteresis there is enough to prevent that continuous cycling. So there's some benefit to that. So let's talk about the advantages of adding a DC to DC converter to your system. First of all, like I just mentioned, it does pretty much alleviate the battery drain cycling issue. The other thing is a high quality DC to DC converter will also provide galvanic isolation. It'll protect against inrush. It'll also protect against overvoltage. It also will provide a 24 volt DC output, which would allow any OCS product to be used, at least from the standpoint of supply voltage. So for instance, an X4 or an X7, which normally could not be used with 12 volt supply, if there's a DC to DC converter converting it up to 24 volts, then they could be used. But of course, there's no free lunch. There are disadvantages. DC to DCs can be expensive. Now you can get less expensive ones, but you're going to get less benefits from them. There's probably not as much hysteresis. They may not be isolated. You may not get the same level of protection. Well, you won't get the same level of protection with a cheap DC to DC versus a higher quality one. And the DC to DCs, especially the higher quality ones that I'm showing on the screen from Pulse, they are also physically fairly large compared with the smaller units that you can get that are less expensive, that I'm also showing on the screen there. So that is one way to solve basically this battery drain cycling issue. The next issue we're going to talk about is engine cranking. So what is that? Well, on the screen there I'm showing you a graph that shows what can happen voltage-wise to the battery or to the system voltage while an engine is being started. And this is exacerbated in cold weather because we all know that batteries don't really like cold temperatures that much. Okay, so the colder the temperature, the more this is exacerbated. So effectively what can happen is, as the engine is started, it can drop well below the OCS's lower threshold, especially if it's cold, and it can stay there for a few hundred milliseconds, and then it can take a few seconds in some cases to get all the way back up to the normal voltage range after the start. So how can we deal with this? Well, first of all, in a lot of applications, this is not a problem. Okay, it's not uncommon during the start of a machine that's engine related for the expectation to be that the OCS is either not on to begin with, or if it resets, it's okay. So it may not even be a problem that we need to solve. But if it is a problem that you want to solve, a component that we can use to do that is something called a boosting voltage regulator. Now there's also bucking voltage regulator, but we're talking about a boosting voltage regulator because what we want to do is we want to take lower voltages that we might be getting from the supply voltage, and we want to boost those up to the point where the OCS isn't going to reset during at least a significant number of these engine cranking type scenarios. So what I'm showing there on the screen, a relatively inexpensive, very inexpensive, frankly, boosting voltage regulator that can handle voltages all the way down to 5 volts. Now it doesn't go all the way down to like 2.8 or 3 volts, which is kind of the lower limit of what you'd like to be able to support to never have a reset, but it will get you all the way down to 5 volts. Now what are the advantages here? Well, as you can expect, it's greatly going to reduce the impact of engine cranking, although it's not going to completely eliminate it when your voltage drops below 5. And again, it also has the benefit for helping with the cycling issue we talked about before. It can also help address that as well. What are the disadvantages? I wasn't able, at least, to find this component as being readily available in packaged form from mainstream manufacturers. The one that I've got that I'm showing on the screen that I'm demoing on my bench, it's one I picked up at Amazon for a few dollars. So I can't say that I'd necessarily want to, install that on a expensive machine, but it is an example of the type of component you can use to accomplish this. All right, so this is the next demonstration I'm going to show you, and that is using a boost regulator in between the supply voltage and the OCS to boost the voltage to the point where we, at least a lot of the time, don't have any engine cranking resets, and we also should almost never have the issue with the OCS doing the cycling because of battery drain. So let's head back to the bench. There's really nothing to talk about from a seascape standpoint. This is purely an electrical solution I'm talking about here. So let me switch over to my bench view here. Right now, I've got the OCS connected to the supply voltage directly. So it's directly connected to this voltage supply. What I'm going to do is I'm going to bring in line this boosting regulator between the power supply and the OCS. So I'm going to power down the OCS because this is the full voltage here, okay, from the supply, and I'm going to replace it with the output from the regulator. All right, let me go ahead and get this plugged in. Okay, so the OCS will need to boot up, and it's going to take a minute or two. Here we go. Well, not a minute or two, but it'll take a few seconds for sure. All right, so the XL4 is booting up. Okay, so now we're still monitoring the supply voltage. That hasn't changed, but the voltage that's keeping the OCS running is now coming from this boost regulator. So let's see what happens when I drop the voltage down to the level at which it reset before, which was what, 9.5 volts, I believe. Okay, so we get down around 9.35 volts. Okay, we're definitely below that level now. Okay, and you'll notice that we're still running. And that's because this boost regulator is providing ample voltage and power for the OCS to run. Let's take a look at what that voltage is. I'm going to go ahead and pull in a multimeter. Let me go ahead and turn that guy on. Select DC voltage. All right, and I'll go ahead and put it where we can see it, hopefully. All right, and let me go ahead and monitor the output voltage from this boost regulator. And you can see it's putting out about 15 volts. Now, the way this regulator works, and a lot of them work this way as well, is there's a potentiometer, or at least some level of adjustment for the output voltage. So even though the supply voltage is currently about 9.16 volts, okay, there's a little difference in the readout between the OCS and the supply itself, but it's around 9.2 volts. And the output from the boost regulator is actually 14 volts. So let's monitor that as we crank the voltage down a little further. And you'll notice that as the voltage continues to go down, the voltage going to the OCS from the boost regulator is holding steady at about 15 volts. Okay, all right, let me go ahead and move this out of the way now. Okay, so let's see at what point the OCS does finally reset with this boost regulator in line here. Okay, it should be somewhere around the 5 volt range, and if we go down slowly, it'll probably go below 5 volts quite a ways. The part that is the main component on the regulator is rated for 5 volts, but its actual performance is a little better than that. Now keep in mind that when you're doing cranking issues, when you're doing a crank of the engine, the voltage is going to drop quickly. It's not going to drop slowly. So you're not going to get this kind of performance under normal conditions. You can see we got down just below 4 volts is when the OCS finally powered down. I'll get it up to around 8 volts now, and the OCS will go ahead and boot back up again. So you can get down to about 5 volts comfortably using a boost regulator like the one I've shown here, in order to kind of solve at least a majority or a significant percentage of your cranking issues with an engine. Let's head back to our material and let's continue on. Okay, the next issue we're going to talk about is something called load dump. So what is load dump? Okay, well, a load dump issue is actually a high voltage issue or a high transient voltage issue. So when a large load is switched off from a 12 volt DC system, it's very often possible that the voltage will jump, at least briefly, until it comes back again into regulation. And this is exacerbated when, or it's in its worst case scenario, when the battery is disconnected from the alternator. Because what happens then is you get a very large voltage spike, and that is kind of what the load dump testing that is done by many manufacturers and the load dump specification that is published, that's what that refers to. That worst case scenario when the battery is disconnected from the alternator and boom, you get this big transient. So how do we solve this? Well, first of all, the good news is that for the non-worst case scenarios, there's already a lot of transient protection built into the OCS power supply circuitry. So in a lot of cases, if it's not that worst case scenario of the battery and alternator becoming disconnected, then you're not going to have the types of transients that you need to worry about. However, if you want to add additional protection for that worst case, you can add an automotive grade TVS diode across the power supply input to the OCS, and that will provide that load dump protection. Now, where can you find a TVS automotive grade diode? Well, you can find it pretty much at any electronic supply store like DigiKey, for instance. I think I picked up the Littelfuse TP6KE20A as being a good potential choice. It is a component that has leads. You know, it's not surface mount, so you'll be able to integrate it in a control system, and it will provide the extra protection needed against some of those worst case scenarios with load dump. So of course the advantages are the additional protection that you receive from a very inexpensive component. You know, we're talking about a sub $1 component. Of course the disadvantage is this is an electronic component in a leaded package, which, you know, takes a little bit of care to be installed in a typical control enclosure type application, but it's certainly not that difficult. You just need to take some care in the install based on the package. So that is how you can solve load dump by adding a TVS automotive grade diode to your system. Let's talk about some additional features that are popular with automotive or mobile type applications, or really any applications that are based on kind of an engine. One of the more popular features is J1939 communications. Now, some of you are probably very familiar with J1939, and others you've never heard of it. And we've done several technical topics and webinars on J1939, at least 2 that I can think of. So what J1939 is, it is a CAN-based communications protocol that was mandated be present on all vehicles from 1996 on. And it's pretty much gotten to the point that just about everything that has an engine also has J1939 included. Okay? And the OCS, including any of the units that have 2 CAN ports, can support J1939 as standard. And if you're talking about an OCS with a single CAN port, like an XL4 or an EXLW or a XL4 Prime, for instance, it's an option that you can acquire to add the J1939 capability to your unit via the CAN port. Okay? By having that J1939 supported, you now have the ability to monitor a lot of data that is being generated by the engine control module, temperatures and pressures and those sorts of things that are just available to monitor without having to add any kind of parallel instrumentation in the terms of sensors and those sorts of things. So the OCS is perfectly capable to monitor that data as well as to perform some level of control over J1939. Now, one of the requirements is you're going to need to have a copy of what they call the PGN list, which is the parameter list for the engine or the device that you're monitoring over J1939. And not all manufacturers are that open with supplying that list or publishing that list. However, a lot of the parameters are common, that are not different from manufacturer to manufacturer. They're common. Therefore, if you can come up with a PGN list, you can probably find the data that you're interested in and be able to monitor that from an OCS over J1939. So definitely a popular feature for sure. Another popular feature for mobile applications is wireless networking. And it's not popular because there's a lot of wireless networks on a vehicle itself or on a piece of mobile equipment itself. It's popular because those mobile machinery and mobile equipment and mobile vehicles are moving around. And so when they need to communicate with a host, that's when the wireless communications is handy. All the networks that are on the vehicles or on the mobile equipment, for the most part, that's all wired because of a very noisy environment and a rugged environment. You want all that to be as wired as possible. However, if you've got some sort of agricultural machine that you want reporting status back to the host, you may want to do that over a wireless network, right? You're certainly not going to tether a cable to your piece of agricultural equipment that's moving around a field. So you might use, for instance, a 900 megahertz radio modem in that scenario. You might use cellular as well. Maybe you've got another piece of equipment that needs to communicate with a refilling station or a refueling station of some sort, and it's going to be pulling up to the station and then pulling away again. It might want to use Wi-Fi or 900 megahertz wirelessly in that scenario. And then maybe you've got a portable generator that can move around, and you may want it to be reporting its status via cellular, for instance. So all of these types of scenarios make wireless communications with a piece of mobile equipment valuable. From a Horner perspective, we offer a really nice, inexpensive Wi-Fi dongle that plugs into any OCS that has a USB-A port, and it can add Wi-Fi to the OCS without using up the wired port that's already there. So if you have an XL4 you want to use with a wireless network, but you also need to use it with a wired network, no problem. You can add the Wi-Fi dongle and you get the benefit of both wireless networks talking to that XL4. If you're looking for a cellular solution, don't directly supply cellular products at Horner. We have in the past, but we just weren't able to continue that for regulatory reasons. But anyway, there are plenty of third-party cellular routers which provide a cellular connection on one side and a wired Ethernet connection on the other side. Those are a great solution for adding cellular connectivity to any OCS system that's portable, for instance. And those are just two examples. And there's plenty of 900 megahertz modems available from a variety of manufacturers if that's the approach you're looking for. Okay, and then finally we'll talk a little bit about video cameras. I think we've all gotten used to things like backup cameras in our vehicles. And so you can tell, or you can imagine, there's some benefit to having the ability to have a little bit of video on an OCS that might be showing something that otherwise the operator couldn't easily see on a piece of mobile equipment. So the OCS supports, any OCS with a USB-A port supports the USB video standard, the same one that's used for webcams, and there's plenty of ruggedized USB cams available from a variety of industrial suppliers that would allow you to add one or more cameras to a mobile piece of equipment and then display the live video one at a time on the screen. Now keep this in mind. Even though you could have, say, up to 4 cameras connected to a USB hub that's then connected to the OCS through its single USB-A port, the order in which those cameras log into the USB hub is going to determine which is camera number 1, 2, 3, and 4. So for better control over that, you would probably want to have the ability from the OCS to turn those cameras on and off to be able to know specifically which camera you're looking at any given time. But again, video cameras are a pretty popular option also in mobile applications. Well, that covers the material that I wanted to cover with you today. And again, I want to thank Bob Lindbergh from Pacific Fishermen's Shipyard for suggesting this particular topic. And we've gotten several requests in from others, and we're in the process of researching those topics, and we'll go ahead and get those on the air probably this summer. Meanwhile, I want to remind you that whether we're live like we are today with the actual live presentation, or whether we pre-record the presentation, We're always streaming live Tuesday at 2 o'clock, and somebody is standing by to answer your questions if you're watching live. And if you're watching on replay, we've also got people who are going to answer your questions, but we're going to answer them from the comment section, and it'll be a little bit obviously longer of a lag to get those answered, but we'll try and do a pretty good job of that. Finally, I do also want to let you know that we've got a fun session for you next week inside the new XL Prime. We're going to do a little bit of benchmarking with the XL Prime and the XL series and just take a deeper dive inside that new product series. For those of you who have seen who attended the launch webinar for the XL Prime, if you haven't done so already, I would suggest that you find that video on our website. Check it out. That's the introduction of the XL Prime. What we're going to be covering in this particular session is we're going to be taking a deeper dive inside, doing some comparisons between the XL Prime and the current XL series, those sorts of things. Finally, I want to let you know that if you haven't done so already, we'd appreciate it if you subscribe to our channel. If you choose notifications, you'll be notified every time we go live or every time we drop a new video, which we do at least once a week. All right. Once again, thanks for joining this week. Get your suggestions in for topics that you'd like to see, just like Bob did, and we'll do our best to get you taken care of. All right. Take care.